Hello, everyone. Welcome to our presentation. We are delighted to welcome you to our little project that we have been working on for like the last couple of months. So we have for you here today a new technique that we have developed, both of us, and it's called Ensemble X. So it's like a recipe for all you all to like combine different neural networks in the deep learning domain, and solve a lot of problems with it. And what will we try to achieve with this? Well, that's what the presentation is for, right? So let's dive into it now. Okay, so my name is Dipam Paul, and I belong from the city of Kolkata in India. And I'm a final year undergraduate student pursuing electronics and telecommunication engineering. And my area of interest has been exactly this: medical imaging and the using deep learning techniques and tools. I've also worked at various labs in and across the world, and this is my first PyData Global, and I'm really excited to be here. And I wish it if it was in person, but well, what we'll have to make do with what we have. So yeah, that's pretty much about me. And there's like a picture of my city there and a little minion there. So that's kind of where I belong from. Now over to my co-presenter.
Thank you, Deepam. That was a wonderful introduction as well. So, greetings to everybody. My name is Alankita Tiwari, and I'm from the city of Lucknow in India. Now, my city Lucknow is famous for its lip-smacking food, its culture, its history, and its architecture as well. And I am also an undergraduate student in my final year and pursuing the same electronics and telecommunications. And my interest in deep learning and machine learning and artificial intelligence is something that was the reason behind Dipam and me crossing paths in the first place as well. Like one of the reasons or one of the things that we connect on. Together, we've like worked on various different projects as well in the last couple of years and everything. So yeah, having said that, I have also had the privilege to work at some different labs and be a part of different conferences all over the world. Whereas this is my first PyData Global as well, and I am also very excited to be here, and I really look forward to this enriching experience. Now, over to you, Deepa.
Thank you so much. So we really thought about, we put a lot of thought into this. So we thought like before, deep diving into what we have done, it's very important to, pay homage or a little tribute to all the advancements that have been made in this particular field of medical imaging. So now I think a lot of you, are already probably familiar with what it is, but I'm sure a lot of you, in fact, I had this curiosity that this probably is, a new world thing, as in, since we have the, privilege of having so much compute in today's world. So we might just, like have tools available to us, such as, different deep learning architectures, etc. Therefore, we are able to, achieve so much with medical imaging. But actually, that is not true. It started out in the late 1800s, and it's been there like throughout an entire century, and it's still going on. So this just proves like how progressive this field has been over the years. And yeah, it does feel quite gratifying in order to contribute in the same field that has had so many scientists, brilliant minds working together. So let's move on. So first, let's look at why did we actually want to solve this problem. I think this is one of the first questions we should answer before deep diving a little into the presentation. So can we move on to the next slide? Correct. So it's very important. So where we stumbled across this problem. So essentially, when we started out, we were dealing with 3 data sets. One was of skin lesions, one was of malaria images, cellular images, and the third one was OCT images. So these data sets have been previously worked on by different authors, and they have worked. They've used like multiple architectures as well in order to validate their results and classify whatever the problem statement required them to. But what they did not solve, except for the accuracy part, were quite a few aspects actually. To name a few, to just give a brief, we'll of course tell you more about it in detail. For example, they did not take into account about model reliability, and that does play a very important role in areas such as this, and we'll know in the consequent slides about how and exactly why it's important. But this is exactly where we stumbled across the problem, and we really thought that combining different architectures together actually could solve a lot of problems than having just one architecture there and have it classify over and over again. So if you can move to the next slide. um, so yeah, now a very important context of the problem from where we come from actually. So we'll talk about the problem of variance. So the problem of variance is, of course, a very important problem that we set out to solve. So as you all know that when we talk about medical images, patients, real time patients, every case is almost special, like at least different from the another. And to rely entirely on a algorithm to solve your problem, that algorithm has to live up to its standards. I mean, it has to be that resilient enough in order to not falter, in order to not produce consistent results. So that's the problem of variance. So it exists, and it's a problem that all of us deep learning enthusiasts are trying to solve. So these are also the problems that I talked about in the previous slides, which like we took care except for the accuracy part. Okay, the second one, serious lack of reliability. This stems from the first problem itself. If your model or if your algorithm falters, or let's say succumbs, or falls prey to the problem of variance, then of course your model is not going to be reliable enough in a real-time scenario, which is again not a very favorable circumstance. Third, a lot of doctors have the misconception, especially what we got to know when we started working on this problem, that they are sort of reluctant to use these algorithms in place of their medical expertise. So there was so they thought that it's like a trade-off. So one day probably the algorithm is going to replace them in the long run. But what we would like to again highlight here is that was absolutely, and that is not the motive at all. And what we want to do here is we want to propose an enhanced form of diagnostic pedagogy, which will work in cohesiveness. So in tandem with the doctors that are there, and it will sort of coalesce with the medical expertise that's in play already, like the traditional way of treating patients, and also use this algorithm to detect various diseases which are probably solvable by the means of computer vision. So we can move to the next. I would request my co-presenter to carry forward with the presentation from here on.
Thank you, Dipam. Thank you for that wonderful explanation as well. Now, talking about what, as my co-presenter up till now talked about why we did what we did, I would like to throw some light upon what did we actually do. So now talking about our algorithm, I would like you to take a little note of the fact that we're using the test case 1, or the OCTX problem that we first discussed about, where there was a data set of OCT images that were essentially used for classifying different types of retinal disorders. So now talking about our model, this is a workflow of the model that we actually build up. So now here, as you can see, what we did was, after the initial data acquisition process, we then pre-processed the data by means of different methods, such as data augmentation, one that was very important in this test case scenario as well, because we faced the problem of class imbalance. So now that was one thing that we had to sort of look after. So after doing all these initial steps, what we did was we took these 3 pre-trained models, which are like mentioned in the workflow model in front of you, and a custom CNN that we built ourselves. And we individually trained these, different data, different models. And why did we choose these model architectures? That is a question that's, there's a high chance of you thinking that right now, that why did we choose these specific, pre-trained models only, when there are literally so many more of these, dozens of these different model architectures already present. So hold on to that thought. We'll be answering that in a short while. So after initial training of these models separately, what we did was, I am quite sure you can see that red circle right there. That is our initial, or that is our main contribution in the entire study. That is our ensemble, model that we came up with, which ensemble, in the literal meaning of the word, like that model actually added up the individual performances of these models and gave us a better model that outperformed almost all of these studies individually. And as you can see, we later tested it on unseen examples in the validation step. Now, moving on, the phase one of this process was the training and the inference phase. Again, we've taken our first test case into account. As earlier, answering the question that I earlier asked you to hold on to, we use these three predefined or pre-trained model architectures because of, one very important fact being they were actually compatible with each other. So when we're talking about ensemble learning, or ensembling different kinds of pre-trained architecture, so that one thing that we have to take into account is the fact that all these different models should actually complement each other and be compatible with each other, and actually increase the efficiency of the entire model. And that is the reason we took these models into consideration, besides the fact of their individual performances being quite remarkable. So other than that, we use the ADAM optimizer after testing some different optimizers such as your RMS prop, and we found the ADAM optimizer to be the most suited for this present study. So that is why we chose the different models and the optimizers that we talked about. Now here is a tabular representation of the different metrics used against the different pre-trained model architectures and our custom CNN, for your better understanding of the kind of individual performances that we obtained by training our models with the individual models with the data set, with the same data set, if I may add. Now, the second phase, the training and the inference, phase two. Now here, this is the the red circle part of the initial workflow that we talked about, the ensemble model, which we in this present study named OCTX. So here, as you can see, we have n number of deep neural networks that were four in the case in the case study that we talked about earlier. So we, depending on their performances, initialized or assigned nonlinear weights to them. After which we designed and trained our ensemble model, freezing all layers except our fully connected layer and the dense layer. Post which we retrained the entire ensemble model. After which we tested it on our test set or the unseen examples, and found the performance or the result to be better than all of these individual studies. Now over to you, Dipam. I would like you to throw some light upon our contributions in detail.
Correct. Thank you so much. That was a very, very brilliant explanation of very concise explanation of what we have actually done here. The how of it, if I may. Now coming to the very objective pinpointing of what we have actually tried to achieve here. So number one, it's sort of it's called the dream of every deep learning enthusiast to attain state-of-the-art accuracy. Any research project would of course try to attain more accuracy than all of its previous studies. And to be honest, when we started out with this project, that was not even our primary aim. Our primary aim was to just combine different neural networks and see what happens based on the experiments that we conduct. This was a result. And why was this happening? This is very important, I believe. So this happens because of a very important statistical theory, which is called central limit theorem. So central limit theorem essentially talks about that if you combine different models or architectures together, your combined model is supposed to yield you better results, better performance in terms of a lot of aspects than all the individual models you can combine. It also talks about as a corollary to that particular principle, as a corollary to that particular principle, that you cannot ever reach the accuracy of perfect one or like 100% accuracy. But I don't think that's like a necessity as well, in order to like conduct a study essentially for research purposes. Uh, Second, we talked about reliability, resiliency, of course, the ability to tackle the variance problem. And now, why does this problem get solved by the model that we generated by combining different architectures together? Okay, it's very simple. So when we have different architectures in the context now, rather than one single architecture is used multiple times, we have to realize that these architectures have very different characteristics as well from each other. And when we put that into account, when we factor that in, we have to realize that the disadvantages too that each of these architectures have are sort of counteracted with the other architectures, which is exactly where my co-presenter talked about compatibility of models. And that has been, one of the more, essential things that we did take care in this particular study, because like I said, resiliency, in my opinion, is more important than even accuracy. Because yeah, in real world, you have so many unseen examples and they keep on coming every day. That's how it happens. So if your model is not resilient enough, if your model is not resilient to changes, to unseen changes or unseen examples it hasn't seen before, uh, it's very problematic. And in order to tackle that very thing, we sort of tried to combine different architectures together and move forward with that, and it was able to solve the problem. Thirdly, we very fortunately enough, again, this was an observation out of the experiments, we have successfully mitigated the chances of overfitting. And we'll my co-presenter will like visually show you via graphical representation how that happened. But yeah, so the overfitting problem has also been taken care of by this particular method that we are proposing here. And I think that is one of the more primary indicators of the performance, and my co-presenter will take on forward from the performance analysis to the results and show you how it's done.
Right. Thank you. Thank you for that introduction. Now, coming back to the performance analysis, here we can see the the confusion matrix in front of us, and how we can see that the accuracy that we got was nearly 98.5%, whereas the misclassification that occurred was close to 1.47%. Now, that is very important to, as my co-presenter earlier said, this is a very important result, or a very important, thing to take into consideration, that actually proves that our study is resilient and is, one that can be over time be improved and be actually applied for clinical, usage in clinical tests as well. Now, moving forward, the convergence and the convergence of train versus validation loss function and the accuracy curve. Again, Dipam, I will come back to you and ask you to take this forward.
Sure. So yeah, like I was saying, so we actually tried to mitigate the overfitting problem, right? And this is the evidence of that. This is the live evidence of that. So like my co-presenter also mentioned, like considering the test case of OCTX, we trained the final model, the Ensemble that you saw, for entirety of 250 epochs, and these are like some of the graphical results that we obtained from the same. And as you can see, like the training and the validation loss curve sort of converge very beautifully. So that was a very interesting observation to note also, because yeah, that sort of tells you how your model does not overfit or are a little bit like resilient to changes that occur during the training process as well. So that, and if we can move next.
Right. Now,
Right.
talking about the representation of results, here what we did was to make this study more, inclusive for all the our research fraternity, and make it more useful and actually concrete for the medical domain, for the people of the medical domain as well. What we did was we instead of going with just one kind of representation of our results, we actually took into consideration two different methods of representing our results and whatever it is that we got because of the study that we performed. Now, talking about the first kind of representation, the grid representation, here we can see that the misclassified images are labeled in red, and that actually, in this random batch. Or random, batch of samples, we can actually see the few numbers of the misclassified images, which again uh, stands as a testimony to the robustness of our study. Now, this particular representation comes in very handy for the people of from the research community or deep learning enthusiasts and everybody who actually want to take away the results of our study in an easier way. Now, talking about the results representation, predicted results representations of test results with confidence scores. Now, this method is very, very important for the, diagnosticians or the medical practitioners, because this actually helps them, get an understanding of the probability of these confidence scores and of the basically the probability of their diagnosis being right in the case of overlapping classes. So this is something that actually proves to aid them in trusting these machine learning or deep learning models. And as we said, as we discussed earlier, one of the problems that we faced was the fact that we found the medical fraternity to be kind of apprehensive towards accepting AI into common or in the mainstream healthcare. So now this is kind of a representation that actually aims towards bridging that gap between the two communities. Now, here is an additional study, the comparative study between the landmark data, between the landmark, studies done on the same data set that we've tabulated in front of you. Here, the first study that I would like to talk about is the Karmani et al. Study, which is a very important study on this very topic of classifying retinal disorders, because this is the study that actually was the one behind fashioning the data set that have been used by us as well. Now, coming to the Rastogi et al. Study, now they actually used a detection system based on deep learning models, and this study is the one that sort of inspired us to come up, take up this specific problem in the first place, after which when we met with the problems that we discussed earlier, we came up with this idea of Ensemble X itself. Now, the third study that is mentioned in the table here is the OCTX study, or the study that has been authored by me and my co-presenter as well. So, as you can also see in the tabular representation, our study outperforms these two landmark studies in all of the three metrics stated. Now, this is again a visual depiction of or a little insight into the papers if you want to read them or get to know them in details. So this is what we've done here. Now over to you, Dipam, to discuss about the plan enhancements and the scope of improvements.
Thank you so much. Okay, so now let's finally talk about the enhancements or areas of improvement that we can work upon, and that there is to work upon in this area. So the first one, let's talk about that. It's I think the most important one among all the three. So of course, there's no thumb rule that exists in determining the number of models that you can use to ensemble different neural networks versus the amount of training data that you have, right? So we have done for example, what I mean by that is, so for the OCT study, we have had used different data augmentation techniques, etc., and we have sort of managed to increase our data set to somewhat around, let's say, 70 to 80,000 images perhaps. And we thought like that but again, there was no formula which could tell us, or direct relation, or even an indirect relation that could tell us that for 80,000 training data you might just use 4 or 5 models. There's nothing like that. It's completely empirical based. And simultaneously, for like the lesion study where we studied skin lesions, we had very few images, around like 12,000 images, and we use 2 architectures there. So there's no thumb rule there, and I think it'll be really interesting in the future if we can come up with something like this. I think it's going to be a very important discovery in this particular direction as well. Second, of course, faster computation with less or reasonable resources, because there's of course a trade-off that I'm sure like all of you listening to this presentation would already have like that have crossed your mind, that when you're increasing the number of models, you're increasing the number of convolutions, you're increasing the number of complexities, naturally your resources or your compute has to go up, because here you're not just training one model, but you're training n number of models together. So that's definitely a trade-off that exists. But yeah, we will definitely but I personally, I don't think this is going to be a problem, given like the kind of advancements we are making in that sphere of resources when it comes to GPU, etc. And yeah, lastly, better optimization. Of course, who doesn't want better optimization? So as more optimized your models are, more compatible your models are together, the better they are. And I think like one of the very important things to mention here would be how we can actually try to develop a particular system of combining these models. We have definitely proposed a system here, and I think that system works. I truly believe, but we should also realize that this system is also very experimental based, as in you cannot possibly reach to the correct number of correct models at the very first go. You have to like go on, and then finally see that this is yielding you the best results, and accordingly go with the same. But if we can actually devise a mechanism to know that these are the models that probably are very, very good together, that will be really nice. But I also somehow believe that these are a little data oriented as well, the learning capability. So can we move on to the next slide?
Sure.
Yeah, so now one very important thing that we would like to mention here about the presentation in general is, so I know this is probably not like the same it would have been had we been there in person, physically in PyData Global, and we would have talked and interacted after our presentation regarding all the probably thoughts that you would have, or we would like to like know more to advance in this particular direction. But we really would appreciate if you write to us in our email IDs, and I know it's probably not the same if it would have happened over a cup of coffee, but yeah, we would really we will of course meet you at the Q&A panel session. But so we saw when we sort of tried to record, like right now when we are trying to record this presentation, what we are trying to do here is, we, instead of like narrating the entire presentation, what we try to do is we sort of try to have these preconceived questions that you probably would have crossed in your mind, and try to answer those beforehand in order to make it a little more seamless, because of course we won't have as much time. So these are our email IDs, and if we can move on to the next slide. Right. Thank you, from the both of us, to the organizers and the speakers and attendees, and of course, like the people of the community who strive to make this community bigger and brighter every day. And if my co-presenter will present her vote of thanks.
Right. Thank you. First and foremost, thank you to my co-presenter here for not only this particular presentation, but also all the research that sort of went behind it. It wouldn't have been possible without you. Now, coming back to this prestigious platform that actually gave a chance to, mere undergraduate students like us to actually dream big and, trust in ourselves to bring about the change that we want to see. So thank you for this lovely, this great opportunity. And thank you for all the organizers. We can imagine the kind of work that goes behind making this conference so seamless and what it is. And thank you to all the speakers and attendees. Again, without people being there and actually being interested in and paying attention to whatever you're presenting or saying, it sort of nullifies the point of that. So again, this wouldn't have been possible without each and every single one of you. We actually will look forward to hearing from some of you, in our emails, and we would love to connect with you through our emails. And again, thank you from my end and my co-presenters' end to making this lovely community bigger, brighter, and more wonderful every day. Thank you.
And we do look forward to PyData Global 2021 and possibly in a physical setting.
Sure, that's there. Yeah, true. Thank you.